All right, hello again. So we're going to continue our talk about nuclear radiation. We're going to talk a little bit more about how we can predict whether the nucleus will be stable or if what types of decay will occur. And then in the end of this discussion, we're going to talk more about nuclear fission and fusion. But first, I just wanted to give you a little food for thought. Yes, the Hulk was formed by exposure of gamma radiation. I'm not sure if that would actually occur, but you can figure that out. You are the future scientist. This is a graphic organizer that's kind of organizing some of the thoughts that we had in our last lecture, and then touches on some half-life information, which you'll cover if you go into geology in college. You already talked about with evolution and fossils in earth science and biology, and then you've got the information here about alpha, beta, and gamma particle arrays, and then just some information organizing atomic number and then isotopes and how electrons and neutrons and protons are all interconnected. So that's just a helpful guide right there for you. Last thing, if you've ever heard of the term background radiation, it's talking about cosmic radiation. And so cosmic radiation can cause certain nuclear decay events to occur in the atmosphere. In this picture here, you're going to see a neutron that's bombarding a nitrogen and a nitrogen-14 particle, which then is going to be incorporated and turned into a carbon-14 particle. Carbon-14 is really, really useful in radioactive dating. Carbon-14 gets incorporated in this plant here from photosynthesis, and then it's going to get eaten by this horse. And then the horse is going to do cellular respiration, or it'll decompose and carry that little carbon nucleus with it. And then later on, it'll decay through beta decay to a nitrogen-14 molecule again. So it's all really connected. It's incorporating a lot of information that we already know. And so this is a great topic, nuclear chemistry. Okay. Picture here is showing you fission and fusion, or excuse me, is just a fusion reaction in the sun. But let's go ahead and start talking about nuclear decay. Okay, so when we talk about nuclear decay, if I ever mention anything about the nucleus being changed, the term that I'm trying to use is transmutation. So it's changing, and it's changing into probably a totally new type of element. So first of all, it's any change in the nucleus, anything. And it's anything that causes one element to become a different element, so maybe carbon becoming nitrogen. And this can be done naturally, it just happens, or it can be man-made or forced by man via different processes that we can do, so we call that artificial transmutation. So this big picture here is showing you how naturally carbon turns to nitrogen, turns to carbon, and then you'll see the gamma particles coming out. You can see an alpha particle being ejected, and so there's a lot of stuff going on here, but it's just turning to different elements. So that's what transmutation is. Okay, so natural transmutation will occur through any of the four types of decay that we discussed in the previous video. So one of those four is going to cause transmutation, cause the changing of an element to become a different element. And so we'd like to try to predict if this is actually going to occur. The only reason this would occur, this decay would occur, or transmutation would occur, is if the neutron to proton ratio is not stable. And so we want to know if it's going to be able to become more stable from its unstable state. So when assessing the stability of a nucleus, you're primarily looking at this proton to neutron ratio. And the ratio is going to be 1:1 up to 1.5:1. So it's neutrons 1, protons 1. So for every 1 neutron, there's 1 proton. Or for every 1.5 neutrons, there's 1 proton. And we know there can't be 1.5 neutrons, but this is just the relative ratio. And so I've got a graph on the next slide here to show you that scientists have discovered that there is a stability of neutrons to protons that occur within this ratio between 1:1 and 1.5:1, and we call that a band of stability. So right here is this graph. The graph in the middle, the dotted line, the black dots on the line right here, that's the band of stability. And this is where the proton to neutron, or neutron to proton ratio wants to be, in between here, for the nucleus to be considered stable, therefore it will not undergo any nuclear decay. So you can see these little black dots. All these little black dots are stable nuclei for all different elements, and they all are falling between the ratio of 1:1 on the low side and 1.5:1 on the high side. But there's a difference between sizes of nuclei and as to which ratio they prefer in terms of stability. So you've got neutrons to proton ratio for small atoms, things under 20, under the number of neutrons of 20, you've got a pretty low ratio, about 1 to 1. It's almost directly on this dashed red line where the 1 to 1 ratio is. And then you've got on the high side, so for larger atoms, it's a different story. So slowly this black pattern, this black dot pattern, heads up to the high part of the ratio, which is a 1.5 to 1 ratio. And so on the high side of things, very large nuclei, it takes more neutrons to keep the nucleus stable. So the ratio goes up to a 1.5 to 1 ratio. And it increases as the size of the nucleus increases. So you also need to know that it's going to be between 1 and 1.5, but when you have very small atoms, it's going to be on the low side of the 1 to 1 ratio, and very larger atoms will be on the high side. But if we let this dot pattern keep going and ascending past this, it's actually going to exceed the 1.5 to 1 ratio. That is very unstable. So everything's going to decay to fall back into the ratio 1 to 1 to 1.5 to 1. So that's the magic number. We got to be between there in terms of stability. This is just another look at a slightly different graph. It's got the banding pattern, the band of stability in the middle and all the way up here. And then you're going to see that there's a couple of examples given to you. So lithium with an atomic number of 3 and atomic mass of 6, meaning you've got 3 protons and 3 neutrons. That's a 1 to 1 ratio 100% exactly. Then you go up a little bit, and we're still in the ratio. We're still fairly close to the 1 to 1 neutron to proton ratio. You get to cadmium. Cadmium has an atomic mass of 110 and a proton number of 48. When you do the math and you take your mass number minus 48, you get a ratio of about 1.29 to 1. It's still stable, but it's starting to get towards the 1.5 end of things. Then you've got all the way up here at the top is mercury. Mercury has an atomic mass of 202, proton number of 80. When you do that math and you minus 202 minus 80 and you get the neutron number and you compare that to the proton number of 80, the ratio is 1.53 to 1. That is like the top. We cannot go past that because it needs to be very, very close to 1.5. Everything past this point will decay. So it's too unstable to be past the 1.5 to 1 ratio. So too many neutrons, it's going to undergo beta decay production. Also, if you're under this, it's too unstable because there's too many protons for every neutron, and so it's going to undergo spontaneous positron production. So there's 2 opposing forces here on either side of the band of stability. Okay, so here's the rules to predicting the stability in the first place. So you know the ratio between neutrons and protons needs to be about 1 to 1 up to 1.5 to 1. And then you also know that things can get too large. So any atom that is too large, and the number here that scientists have discovered to be too large is anything above atomic number 83. That is definitely going to be radioactive, therefore it will undergo decay. And also, if you're wondering, there's always an exception to the rule. You've got technetium, which is atomic number 43, and you've got promethium, which is atomic number 61. These are both also always unstable. There is no stable isotope of these particular ones, and I know they're under atomic number 83, but there's always an exception to the rule. We just have not naturally found any isotope of these that are not radioactive. And I've also written up here, we know that these 2 in particular are going to be radioactive at all times. Just FYI, promethium always grows blue-green because it's radioactive and it's expelling certain wavelengths of light. And then technetium is a stellar matter, so it's related to cosmic radiation, so that's also radioactive. Those are just 2 interesting points. I also wrote up here lead, which is number 82, atomic number 82. That's the last of these stable large atoms. And we're going to talk about that a little bit more when we talk about uranium-235 undergoing decay until it gets to lead, and then it sits there because it's stable at that point. Okay, 2 other things that are also kind of trends that we found in stable nuclei are whenever you have even numbers of protons and or neutrons. So it's great if you could have an even number of both. For some reason, the nucleus likes to be in the this magic kind of even number theme, and so this is just one tidbit of knowledge that is a little bit extra helpful in determining if the isotopes are going to be stable. And then we come to the magic numbers. The magic numbers that scientists have designated to be the most stable in terms of numbers of protons, numbers of neutrons, or a combination of protons and neutrons are the numbers 2, 8, 20, 28, 50, 82, and 126. And I know what you're thinking. You're thinking this is magic, this is alchemy, but no, this is just something that scientists, they don't have a great explanation for this. They just know that this trend has been observed. But this actually relates to nuclear shells, and it's in the structure of the nucleus and how it becomes very stable. It's called binding energy. And so the numbers of protons and neutrons with these numbers are just very stable. And so if a particular large nucleus is decaying, it might stop at the combination of protons number 82, which we have as lead, which is also one of the magic numbers. So laugh all you want, but you definitely need to know A and B right here. 100, you just have to know these. But C and D are just trends that you need to be aware of. This is that decay pattern I was telling you about with uranium-2. This is 238 actually. And so it undergoes decay, decay, decay. You'll see the alphas and betas all the time. It's got different half-lives for each daughter particle isotope produced. And then as you slowly get down here, you'll see that it ends at lead, which is atomic number 82. And so that's when it is stable at that point. So that's just another helpful hint to show you that this does actually occur and it does stop at a stable nucleus. Okay, so now we know how to see if something is unstable, if a nucleus is unstable. Now you've got to take that knowledge and you've got to go further. You've got to tell me what kind of decay process that this nucleus could undergo in order to become stable. And so this is the first one. If you've got a scenario where your nucleus is unstable and you find that you've got too many neutrons, which is causing it to be unstable, then the ratio is too high. So you've got maybe a 2-to-1 ratio. You've got for every 2 neutrons, you've only got 1 proton, which decreases the stability. This is above the stability belt. So you want to increase the number of protons or lose the number of neutrons. And this is done by beta decay. And if you remember from the last lecture, beta decay is where a neutron is going to be transmuted or changed into a proton and an electron, which will increase the proton number and decrease the neutron number at the same time. So it's going to go undergo beta decay until it gets to a stable ratio of neutrons and protons. Opposite of that, maybe your nucleus is unstable due to having a very low neutron to proton ratio. So there's not enough neutrons to offset all the protons that exist. So this is below the band of stability. So therefore you need more neutrons or you need to decrease the number of protons. And this, the way that this is done by electron capture or positron emissions. In this case, you got your protons in both of these scenarios being changed into a neutron. So you're going to increase your neutron number while decreasing your proton number, which will allow you to get to the appropriate ratio. Okay, now in this case, you just have something that is too big. You've got both too many neutrons and too many protons. This means your atomic number is greater than 83. This is a very large nucleus, and it's just not stable that large. So it needs to lose as much mass as possible. And the way that it can lose as much mass as possible, meaning you need to lose both protons and lose neutrons. You want to lose both of them at the same time. Well, that is alpha particles being decayed out. So that means you want to get rid of the 4 AMUs or atomic mass units being 2 protons and 2 neutrons at the same time, and that's the fastest way to get to a stable nucleus, which is alpha decay. Alright, so next slide we're actually going to be predicting, so this is on your notes. So we need to figure out, first of all, if this nucleus is stable, the one that's given to you, the 4 examples here, and then you need to figure out what type of decay it would undergo if it were unstable. So your thought process includes these couple of questions. First, you look at it and you figure out, the easiest thing to see is if the atomic number is greater than 83. You know if it's greater than 83, then it will decay because it is very unstable, it's too big. And then you can figure out what's the proton to neutron to proton ratio. Is the neutron to proton ratio too large? If so, beta decay. If it's too small, proton emission or electron capture. So you need to do the math there and see if the ratio is good or not good. So looking at our first example, you see that you've got fluorine, you've got the atomic number 9, which means you have 9 protons, and you've got mass number 20, which means you have 20 mass. So overall, you've got Alright, after doing the math, overall, you're going to see that you've got 11 neutrons and you've got 9 protons. So this is a little over a 1-to-1 ratio. And since this is a fairly small atom with the with lower than or 20 or lower mass number, then it absolutely needs to be a 1-to-1 ratio. So since it has a little more than a 1-to-1 ratio, it needs to lose some neutrons. Neutrons being the 11 there in that case. So you want to lose a neutron, or 2. And so to do that, you need to lose the neutrons by beta decay. So just make sure you do the math right and you compare and contrast the neutrons to protons. And then if it's a very small nucleus, it needs to be a 1-to-1. If it's a very, very, very large nucleus up to 82 atomic number, then it needs to be a 1.5-to-1. So let's keep going. Let's try this next one. Looking at calcium, you can see that its atomic number is 20, and you can see that its our proton number is 20 due to its atomic number. You can also see that 40 being its mass number should also have 20 neutrons because you do 40 minus 20. So doing that math out, 20 to 20, you can see that it has a 1-to-1 ratio, and this is a very stable nucleus because of your atomic number 20. That's a fairly small nucleus, so it should have a 1-to-1 ratio of neutrons to protons. All right, californium. You've got atomic number 98. Automatically, first thing you see is that has a atomic number greater than 83. So you already know that it's unstable. But now you need to figure out what kind of decay process it will undergo. Well, it's got 251 mass number. It's already huge, so you want to get rid of mass as quickly as possible. And the way you do that is through alpha decay, because you can get rid of 4 mass units at the same time. And so remember, that's a helium nucleus because you can get rid of these things very quickly by emitting a helium nucleus. All right, last one. Here we have a fairly small nucleus. We've got a nucleus that's 69, which is lower than 82. It's not fairly small. So it's okay, but now we need to actually check out our proton and neutrons and figure out what their ratio is. So first we've got 69 protons. And then taking the mass, you take 168 minus 69 is equal to 99 neutrons. So when you throw these in a ratio and you calculate, this is what you get. you have a 1.45 to 1 ratio. So since this is a relatively large nucleus, it is okay to be close to 1.5, but 69 is not that close to 82, considering the ratio is a fairly small range between 1 and 1.5. So this is one that's not as easy to understand, is not as easy to estimate, but if you have some support behind your explanation, you're in good shape. So it may be considered to be too high of a ratio since 82 is the largest at 1.5, and 1.45 is very close to 1.5. So in my opinion, this nucleus is unstable and needs to lose neutrons because you want to decrease that ratio just a little bit. We're not going to say how much because nobody really knows. We're just going to say that it needs to lose neutrons to decrease that 1.45 value. So the way you lose neutrons is via electron capture or positron decay. And this is just another description of the graph showing you that very, very large nuclei above the 82 value are going to undergo alpha decay. Ones that have too high on this side, on that side of the stability line of stability, those are going to undergo beta or electron capture. And opposite of that, you've got beta decay, and so on the opposite side, that's actually positron emission. Sorry, I said beta, but you've got beta decay underneath if your ratio is too low. All right, last bit here. So fission and fusion. I know you're gonna make it. You're gonna make it all the way through this lecture here. Fission and fusion. These are terms that you probably have heard of before. You may know a little bit about energy production. You may know a little bit about solar fusion reactions of hydrogen nuclei in the sun. So let's go ahead and go through some of these. So in nuclear processes, we can actually artificially do both of these types of reactions. No, it's not easy, but these are artificial on Earth, so these are man-made phenomena in the lab. And fission is not a natural process. It will, I mean, it could occur out in outer space, but we don't know, but on Earth it's not going to occur. We have to force it to occur by neutron bombardment, which it sounds like neutrons hitting the thing, the actual element, bombarding it. That's exactly what it is. You have this neutron here, and that neutron is going to hit a very, very large nucleus. Example here is uranium 235, which is atomic number 92, which is unstable. I know this is unstable because it's got a number greater than 82 as the atomic number. So we have to entice this nucleus to actually do this. We have to entice it to smack into and bombard this uranium 235. So whenever this happens, this neutron gets sucked into the large atom, and now it is even more unstable. So it's even more unstable. So it's like very unhappy, and it's going to split. And so this is unhappy, and it splits into two similar sized pieces. And I know you're going to look here and you're going to see barium and krypton with atomic numbers 56 and 36. You're saying, oh, they're not very similar sized. They actually are in the overall scheme of things. And along with these two similar sized pieces being broken off are a couple of neutrons that are being ejected as well. And fission is a process that emits lots and lots of energy. This is like why we like to do it. We like to do it because we like to harvest this energy. And so this is actually very economically valued due to the fact that we would like to find new ways to produce energy. So know one, that alpha decay is not part of this at all. Alpha decay, whenever you emit a nucleus, a helium nucleus with atomic mass of 4, that is very, very small compared to one of these kryptons or bariums. So that's actually, some people get that confused. They say, oh, well, this is going to be emitting an alpha particle. That's too small. So the key words here are two similar size pieces. All right, so let's do an example here. This is the equation of the reaction that you just saw on the previous slide. You've got uranium 235 you've got a neutron. And the way you know that's a neutron is because, one, it's got an N, which tells you neutron. Two, it's got an atomic mass of 1, because neutrons weigh 1, and it has a 0 charge. No protons or electrons involved with it at all. As it decays into krypton-92 and barium-141. You can see their atomic masses listed there as well. And then this weird thing you've probably never seen. That's what was on the previous picture listed as neutrons. So you need to know that, one, that's the notation for a neutron, and two, that 3 in the front is a coefficient. And the neutron has 1 mass, 0 charge, so it doesn't change the atomic number at all. And you're going to see a couple of other general formulas which are represented right here, where U-235 is going to be undergoing neutron bombardment. It changes into X and Y, which are similar sized. And then that B represents coefficient. And then it's going to tell you how many neutrons are actually being expelled in this reaction, along with energy production. And so in this case, our neutrons can vary between approximately 2 and 3, where B is that coefficient. So it's going to be between 2 and 3. With the average value being about 2.47, and of course we know 2.47 neutrons cannot be emitted. We're going to be between 2 and 3, which is just the average value here. And then I just told you lots of energy is going to be expelled or released in this type of reaction. This is because the previous nucleus, the huge one, was very, very unstable. And as it splits into 2 more nuclei, which are smaller, those smaller nuclei are more stable because they meet the ratio. And as they themselves are more stable, they're not going to incorporate the energy from the previous unstable nucleus, and so that energy is released and expelled into the environment, which we can harvest. So less energy is needed to hold together those smaller nuclei, so the extra stuff is released. And then you'll notice that U-235 and plutonium-239 are the most commonly used ones in fission. Okay, so now we're going to talk about nuclear power plants a little bit before we actually talk about fusion reactions. So in a controlled nuclear power plant reaction, we actually want to get this energy from a fission reaction. And so how do you control it? Well, that means you need to control the number of neutrons that are floating around, because you only want a couple of neutrons that are going to be bombarding, and then you want to control the neutrons that are produced with, you had 2.47 neutrons produced. You want to control that number so it doesn't go out of control, because as you can imagine, things going out of control is a very bad thing in a nuclear power plant. So this is how this is achieved. You control the number of neutrons and you help them interact with other nuclei. The way you help them interact with other nuclei is you slow them down, you cool them. And so as you cool them, which seems counterproductive, you think that they're being very slow, but when they're really slow, they actually feel the interparticle attractions. They feel attractions to other things more often, so they actually can collide with those and cause a reaction to occur, which causes them to interact. So the way that most of these nuclei bombardments are achieved in a nuclear power plant is from heavy water, which this is water that contains an isotope of hydrogen that has a neutron as well as a proton. So this is what heavy water is. You've got this deuterium, and deuterium, which has a total proton number and neutron number summed together be 2, that's why it's heavy. It contains 1 more mass unit than it should, because normal water has a hydrogen isotope right here with just 1 proton and 1 overall mass unit because of that 1 proton, because there is no neutrons involved at all. So regular hydrogen is just a 1, H1, and then deuterium is making heavy water, which is H2. This is just a term you need to be familiar with. So going back here, heavy water is one of the most commonly used isotopes to help with neutron moderation so that you can cause a reaction to occur. Another way to control fission reactions in a nuclear power plant is through neutron absorption. So you have this fission reaction occurring, And then whenever you produce these neutrons, you want to absorb those neutrons and remove them entirely from the reaction site, also called the reaction vessel. And the way that you actually take away those neutrons that are produced is that you use control rods and you lower it down into this reaction vessel. The neutrons are absorbed into the control rods, and then the control rods are pulled back out of the vessel so that those neutrons are no longer available for reactions, which means they're no longer available for neutron bombardment to force a fission reaction to occur. So the control rods are usually made of things like cadmium or other heavy metals because you want something that's going to actually absorb all the neutrons and not allow them to escape again or not allow them to react again. So I've got a picture of that on the next slide. Oops. Okay, so here's our simulation of what a nuclear power plant looks like. You can see here that this is the reactor in this big kind of oval shaped right here, and then there's water in this reactor. There's also natural things in there, or excuse me, nuclear decay materials, maybe uranium, maybe some other radioactive isotopes are in there. Something really heavy and big because you know that this is neutron bombardment. The orange things here and kind of where the reaction can occur, and the control rods are the reddish colored ones, and those control rods can be lowered down into the reaction vessel as needed to control the reaction. Okay, so this is what happens. The reaction occurs here. It occurs in that water, and as it's occurring in the water heats up because it's the energy is being expelled and released into the water. So this water gets very hot, very, very, very hot. So then it doesn't just get to go out into the environment because that would be thermal pollution. That water gets transmitted and moved through this here. And it moves into another reaction site where it's kind of got some coils right here. And those coils allow for the heat energy from the water to move through diffusion into a different water tank. So the water with the radioactive elements never gets exposed to other types of water. It stays in a loop. So you'll see that this continues. And that radioactive toxic water, I guess you could say, gets put back into the reactor vessel. Okay, the most important part here is that this coiled area where the heated water comes through, it actually heats up the surrounding water, and then that heated water turns to steam. Now, this is like any other electric power plant or hydroelectric power plant where steam is used to turn turbines. And the kinetic energy from the steam turning the turbines is going to be transmitted into electricity, and then that steam gets returned back into liquid water, which then gets pumped back into the area where the steam will form again. So it's all a big loop, and everything is contained very, very well. The big problem is, what if this goes out of control? And we all know what's happened before. Sometimes a reactor blows, sometimes control rods don't work, sometimes things get overheated and there's a reactor meltdown. And then another example of that would be atomic bombs, which we'll talk about in just a minute. All right, so this is the process that nuclear power plants are going to actually be taking advantage of. It's where the neutron hits the nucleus. The nucleus can be split into two other large atoms of different elements, which then form two or three more neutrons, which then hit another atom, which then form more neutrons, which then hit more atoms. So this is actually called a chain reaction, a nuclear chain reaction. And it's a chain reaction because these neutrons keep bombarding and keep hitting things, which keeps causing other reactions to occur. How do you stop it? You take away the neutrons, nothing can bombard, nothing can decay. And so this is pretty much what they've done. They take the nucleus, and it's talking about critical mass and subcritical mass and supercritical mass. Too many neutrons escaping this reaction means the reaction cannot proceed. This one has a lot of neutrons interacting and causing multiple chain reactions to occur. So this is where a lot of energy is going to be being put out, and sometimes this can go wrong. This is actually what we try to take advantage of. This is what we want in a nuclear decay mechanism inside of a nuclear power plant. Okay, Fusion, last thing, this is mainly two smaller nuclei fusing together. It's something like in the sun, this is which is a natural process in the sun. Two helium nuclei can form a hydrogen nucleus. So for very light metal elements, usually gases, the stability will actually increase when you increase the number of neutrons to offset the number of protons so that you have a better ratio. As this occurs, the energy is released when two nuclei come together to form a larger one, because that larger one is actually more stable than the two previous itty-bitty ones. Because two itty-bitty means that you're not very stable because your neutron to proton ratio is not stable. So we actually take advantage of this occasionally as well. We can actually do thermonuclear reactions, and we can only do this at extremely high temperatures. Temperatures such as 40 million Kelvin. This is why this occurs in the sun and not on Earth. There is one instance that I'm going to get ready to tell you about that we've actually achieved this. It's very, 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 very difficult though. Okay, so yes, it has occurred on Earth. Very limited though. So one, hydrogen bombs can actually use both fission and fusion. One causes the other. And so we have seen this on Earth. And then this right here, this kind of circular mechanism here is actually a tank, a device that's including deuterium and tritium, which deuterium was the heavy water hydrogen isotope, and tritium is another water isotope. And these actually can come together, two small nuclei can come together to form a larger helium isotope, which is a larger helium nucleus. This is very difficult to achieve though. So the interesting part about this is what they had to do is they had to magnetically magnetize this chamber to actually hold the two isotopes there in contact with each other without them touching the sides of the container, because them touching the sides of the container at this temperature would melt the actual metal container that they are contained in. And so the way they did this was with magnetic forces and magnetic fields to actually try to force them to react by using that property of matter. So they had to suspend it, and they were afraid that if they touched the sides of the container, the isotopes would cause the entire container to melt, and there'd be a big meltdown. So the reason they want to get this and cause this to occur is because of the energy output that's very, very valuable economically. But what's happening is it's taking more energy to run this machine than it is being energy put out, and so it's kind of not paying off quite as quickly. But some scientists are actually still working on this so they can figure out how they can make this an efficient process so we can actually take advantage of this. Okay, oops, sorry. We're actually going to stop this. We're going to move on to half-life in just in the next video. If you have any questions, ask me as you can, and then also don't forget to do your problem sets.